Okay, this is going to be a look at free body diagrams and how we use them to identify and describe the forces that are acting on an object. So when we talk about free body diagrams, there's some standard components that we have to have, and they're listed here. Each of them is a dot, so regardless of what our object is, if it's a book or a person or whatever it may be, we represent them with a dot as the center of their mass, and that allows us to just represent one object. So we're always going to take whatever it is and represent it as just a dot. We don't need squares or anything to represent them. And so in addition to that, we also have vectors, and if you remember from our discussion on forces, vectors are these arrows that we have, and they have both a size or a magnitude and a direction. So in this picture we've got three arrows of different sizes in different directions, and so that helps to identify each of the different types of forces that we have on our object, which we've represented as a dot here. And so these arrows, their length tells us how big that force is, and their direction tells in which way it's pushing or pulling. So the longer the arrow, the greater the force, and they are proportional, meaning this one is about half the size of this one, so that we would expect this force in newtons to be about half the size as well. And then we have our labeling, and we'll do some examples here, but our labeling is done in a specific way. First, we label the type of force, which we generally do as a large letter, and that could be things like gravity, that could be friction, that could be the normal force, any of those. And then we identify it's acting on which object. So for example, if this is a book, we're going to say that this is a force of a push or force of the hand on the book by the person. Okay, so that's what this on and by means. It's the first one is on. You tell us which object the force is acting on, and then with the other one we identify by which force. So if this is a book, it's being pushed by a hand, and then we're going to say it's a force by the hand on the book by, and it's by this B would be labeled as an H. So we're going to do several examples of this on the next couple pages where you can get an idea of how this works. Okay, so we're going to look at a couple examples of drawing a free body diagram. So let's say that we have a book at rest on a table. So like we talked about, we're going to shrink that book down to a single dot. I'm going to represent all of it as a single dot, and we're going to draw arrows off of that dot to show the direction and the size or magnitude of that force. So forces that are on that book. The first one we can always start with, except for in rare situations, is gravity, and we know that that is downward. Okay, so we have this book, it's got this force of gravity downward, so we want to label that the same way we talked about for our free body diagrams in the previous page. So we're going to label it with a G for gravity, because that's the type of force that's acting on it. It's gravity. It's acting on the book by what? Well, that gravitational force is coming from the earth. Okay, so this tells us that we have gravity. It's on the book by the earth. Okay, so the next thing we have to ask ourselves is, are there any other forces on it? So up here we've got this tip right here that says it's at rest. If an object is at rest, it has no motion, that can be a clue to us that it's balanced forces, it has no net forces acting on it. So what we know is we have to have a force that's the opposite direction, but also the same magnitude or size as this gravitational force. So since it's resting on something, that contact force is what we call the normal force. You get the same normal force when you're sitting on a chair, or like you're pushing up against a wall. of those things are normal forces. Okay, so we label normal forces with a capital N. That's the type of force. It's the normal force. And again, it's going to be on the book and by, in this case, we can call it the table. Okay, so it's the normal force on the book by the table. So that's our free body diagram. And then we can look and see, are there any other forces? Are there any left or right forces acting on it? And in this case, there are not. So that covers us for that one. So let's continue on to our next example. Okay, so in this one we have a girl is suspended motionless from the ceiling by 2 ropes. Okay, so it might be a trapeze artist or whatever. She's hanging from the ceiling by 2 ropes. So again, first thing we're going to do, we're going to shrink that girl essentially down to a single dot and just represent it as a dot. Makes it a lot easier to draw. And again, we're going to think of the forces that might be acting on it. So again, we know there's always going to be this downward force of gravity. So we're going to have the force of gravity on the girl. I'm going to do lowercase just to differentiate it from our capital G for gravity. Okay, so the force of gravity on the girl by, and again, we're going to have the earth. Okay, so we've labeled it. It's the gravity on the girl by the earth. Okay, and again, we look here, another clue we've got is she's motionless. So she's at rest. That's very similar to us saying she's at rest. Okay, the difference here though is we've got 2 ropes. Okay, so somehow we're going to have to balance this force, this downward gravitational force, with the force from these 2 ropes. Now remember, for her to be at rest, the same amount of force downward has to be balanced by the force upward. So we can assume that the force between those 2 ropes, they're splitting that force. So our magnitude of these downward arrows, the size has to be half as much because we have 2 of them. So let's draw 2 arrows upward that are half the size of our downward force, our gravity or our weight, and those represent our ropes. Okay, so what type of force is this? If you noticed in the beginning we talked about types of forces. We have a tension is our force that deals with ropes or strings or cables or anything like that. So we have the force of tension, and we're going to say it's on the girl, and I'm going to keep it the same because we've got our lowercase g down here. By, we can say R by the rope, or we can even say by R1 for rope 1. Okay, so let's label this one. It's going to be very similar. It's the tension on the girl by the rope, and in this case we'll just call it rope 2. Okay, so that's our free body diagram for this situation. Okay, let's look at one more example. And so we've got a rightward forces applied to a book in order to move it across a desk at constant velocity. And we're supposed to consider or include frictional forces. Okay, so this one's a little bit different. Let's start the same though. We're going to have our book represented as a dot, and we're on Earth. I mean, all those things are the same, so we can have gravity. So let's do our downward gravitational force, and again we'll do capital G for gravity. It's on the book, and it's by the earth. Okay, now a few things that are in here. Before we had motionless and we had at rest, and that helped us, but here it's moving across a desk at constant velocity. Now when we talk about Newton's second law, we talked about acceleration, right? And if we have unbalanced forces, we have acceleration. And in acceleration, our velocity is always changing. In this case, our velocity is constant. Okay, so that's our clue here. This is the thing that's going to tell us what we need to have. If we have constant velocity, it tells us that we don't have unbalanced forces, because if we have unbalanced forces, we're going to have acceleration, where our velocity is always changing. It's getting faster and faster and faster, or slower and slower and slower. Okay, so we are going to have to consider again that we're going to have balanced forces here. So all 3 of these examples, we've got balanced forces or no net force. So probably the easiest place to start is we know that the book is not moving up and down, right? So we know that we're going to have a balanced force upwards. very much like our book sitting on the table. We're going to have a normal force that counterbalances our downward gravitational force. So it's going to be the normal force on the book by the table. Sorry, that disappeared. Let me redraw that. Okay, so I've got that all redrawn. Okay, so now let's consider our right and left forces. So it says it's a rightward force is applied to a book in order to move it. Okay, so we're going to call this force, or we're going to call it applied force. We can use either one of those. We'll call it applied in this case. Applied is good when we have, a hand pushing something. It's, something's hit by something else. We can use applied. We don't, there's not a hand force. There's not a, hammer force. We'll just call those applied. Okay, so there's an applied force on the book by, and it doesn't tell us what's doing it, but we can make some assumptions and say it's, we'll say it's a hand that's pushing that. Okay, but we notice here again we've got constant velocity, so this has to be balanced. But down here it tells us frictional forces, and if remember, frictional forces always oppose motion, right? You go to push something across the table, the friction is going to be pushing the other direction. Okay, friction doesn't push unless there is some motion happening or some force that's trying to create some motion. So in this case, we're going to have an equal force in the opposite direction, and it's going to be friction. Okay, and I'm going to do a lowercase f just to identify it as friction instead of, if we had done over here, just a force. Okay, so we could use either one of these. Either one of these is fine for this. So over here I'm going to use a lowercase f just to distinguish that for friction. This also applies when we write friction in equations. We use a lowercase f, so it's a good idea to use that. So we've got two types of forces. We talked about frictional forces. We've got static friction and we've got kinetic friction. And kinetic friction is when it's moving, and static is when it's the frictional force is too strong and we can't start that object moving. So we're always going to annotate this with a K for kinetic or an S for static. So we've got friction, but it's kinetic friction. It's on the book, and we can also say that this is by the table. Okay, so that's our complete free body diagram for this. And one thing I want to point out, if we'll notice, is that on all of these, a way we can check if we've done it right is if our first letter matches the same. Because they're all acting on the book. We shouldn't draw any forces of the book acting on anything else, because we're only concerned about the forces on our book. Okay, so we've got normal force on the book, frictional kinetic force on the book, gravitational force on the book, and applied or force on the book. Here's your examples.